So I think probably not all of you heard that for this session, so there's two barriers. The first barrier is that I'm speaking in English, and the second barrier is that there is a dress code for the session. And some of you got the memo, but not all of you didn't. So if you're wearing an I Made Quarkus 3 t-shirt, put your hand up. Hooray! For the rest of you, well, just this one time, we'll make an exception. But for next time, make sure that you've got your I Made Quarkus 4 t-shirt, or I'm afraid I don't make the rules. So the first question, why are we here? Possibly because all of the other session rooms are full. It's, it's challenging to get into some of these rooms. But hopefully that's not the reason. Fundamentally, you may have noticed, the world has a rather serious problem. It's getting warmer. It's continuing to get warmer. That's already causing problems. It's going to cause a lot more problems. I don't want to start with doom, but I think for us in IT, this really matters because we tend to think of flying as the poster child of an environmentally destructive industry. But if you look at how much carbon the digital world emits, so that includes IT, it also includes things like the devices that we use at home, it is more than aviation. So actually, it's not the people who are flying who are the problem, it's us. Oops. Now, I did mention that this includes things like devices. And so we could say, okay, well, I don't work in hardware. I don't make devices. So actually, this isn't my problem. But if you look just at data centers, which clearly is our problem, because we're the people who write the things that run in the data centers. And if you look just at data centers, they use as much electricity as a medium-sized country. So they use, sort of a bit more than South Korea, a bit less than the UK. And when you think about that, that's just the hardware, the software running in the data center. But the other thing that data centers do a lot of is network traffic. And when you look at the network traffic, you can see that that goes from that dark gray bar to the light gray bar. So at that point, it's more electricity even than a larger country like Brazil. And the reason network traffic uses electricity is because the network is actually made up of other computers. So when the data goes along the network, it's just hopping from computer to computer, each one using electricity. So that's kind of terrible and kind of depressing for those of us who work in IT. But I think actually this isn't the right response. How many of you were in the keynotes this morning? Yeah, most of us. I thought they were so good. And you can see I've just added this slide after seeing the keynotes, which is, I think it's really important that we be, instead of sort of surrendering to despair, we have to be optimistic. And the reason for that isn't, like we heard this morning, it's not that everything is great. The reason for that is when you look at people who deny the climate crisis, their solution is to do nothing. When you look at people who are so anxious about the climate crisis that they think nothing can be done, their behavior is to do nothing. So you end up in this situation where actually, if you're too miserable about it, that doesn't fix the problem. If you're too happy about it, that definitely doesn't fix the problem. So where we need to be is in this middle ground, where instead of going, ah, please don't do that. We try and find solutions. And so there's this idea that, we need to be a solutionist. And the good news is that actually there are a lot of things we can do, and there's a lot of benefits to doing it. So if you just sort of frame it as a question of like, hey, should we reduce our greenhouse gases? The answer is like, yes. It's the right thing to do. But then as well, if you know, if you're not one of the people who are above average in terms of their morality, like we heard this morning, there's actually a lot of business benefits to it too. It lowers costs, so there's a business benefit already. But as well, now increasingly, businesses have to report on their ESG, their environmental and social governance. And so you want to be part of that solution for your business because it's something that your CEO is going to be caring about. So that means because every business is having to report on ESG, that means when they make their buying decisions, they want another company that's going to not contribute in a negative way to their ESG. So it's this competitive advantage. And of course, it's also a recruitment advantage as well. Because when we're thinking about our next job, do you want to work for the evil company or do you want to work for the company that's saving the world? You want to work, if everything else is equal, of course you want to work for the company that's not evil. So being able to demonstrate that you're not evil helps with recruitment. And so this is the sort of the why is clearly a good thing to do. But then the next thing is, okay, so if I want to fix it, what do I do? There's a number of frameworks available. One of the first was the Principles of Green Software Engineering. There's also the Green Software Foundation, have another framework. Ultimately, it all ends up meaning more or less the same thing and guiding more or less the same actions. I like the Green Software Foundation one, but when I first did these slides, I was working from the Principles of Green Engineering, which to me are a little bit harder to digest. It's very comprehensive, it's very accurate, but that means that there's 9 parts in it. And I don't know about you, but for me, 9 parts is a little bit too much to hold in my head as a sort of if I'm deciding what to do and then I have to go through a list of 9 things, it's too much. So for me, I've tried to reduce it to something that I can hold in my head. So the first thing is to look at the electricity source. Electricity seems like something that's quite pure and quite clean because it's just little electrons moving along, but quite a lot of the world's electricity is generated by burning fossil fuels. And in fact, quite a lot is generated by burning coal, which is one of the most destructive fossil fuels to burn. So when you're thinking about where to host your workloads, the location matters a lot because some parts of the world run almost entirely on renewable energy. Some parts of the world are almost exclusively dirty energy. So, for example, in the Nordics, it tends to be a lot of renewables. In places like South Africa, much less so. So there's a site that is electricity maps, and you can go there, and you can actually it's quite fun to play with the site. You can just sort of go and you can browse and you can see the electricity mix for each region, because each region has a characteristic electricity mix. One thing to note in particular is that Virginia, if I go back, you can see sort of there, that sort of medium brown one. A huge amount of the world's data centers, particularly in North America, are located in Virginia. And there's 2 reasons for this. One is it's where the transatlantic pipe comes out, so then it's really logical to have your data close to the pipe. And the other thing is Virginia is very rich in natural resources. And in particular, it's rich in coal, which means it was able to provide electricity for these data centers. And it seemed like a really great idea until people thought about it a little bit more and went, wait a minute, now we have the majority of the world's data centers running on coal. Perhaps that wasn't such a great idea. So definitely, this is such an easy thing to do. When you're choosing where to host your workload, look at the sustainability information. There's going to be other things as well, like data locality. But even within Europe, for example, there's differences. So choose a region which is sustainable. The other thing, it's getting a lot better. But it used to be that you had to do a lot of homework yourself in order to figure out how green the hosting was. The cloud providers are now starting to report this, and I think it's because of pressure from consumers who are saying, hey, you need to make this information available to me. The other thing to think about is the time of day. So, obviously, the sun only shines part of the time. So if you have solar-powered electricity, if you run at night, it's going to be not green. If you run in the day, it will be green. With wind power, it's usually reversed. Something like hydroelectricity, it tends to be fairly stable. But most of the green data sources, green energy sources, have this problem, which is that they're good at some times of the day and not other times. So use this information to figure out when the best time to schedule your workloads is. Some workloads, you have to be doing it when the user's doing it. Other workloads are batch workloads. You can run it any time. So doing this, it's called being carbon aware with your dispatching, that know what's going on, know what your energy source is, choose the right location, choose the right time of day. And this is kind of a really interesting thing, I think, because in order to be carbon aware, you have to have the right data about, okay, well, where's my energy coming from? What are my users doing? What are my requirements? So there's the orchestration aspect of I need to get my workload running in the right place, which is something that we all love. And there's the data problem of let me get the right information. So this is actually a really fun, interesting technical problem. The next thing to look at, once you've got your hosting sorted out, which was just a free win, the next thing to look at, the model that makes sense to me is to think in terms of 4 vowels. So the first 2 are elasticity and utilization. That's 3. Then the next one to look at is efficiency. And the final one to look at is utility. So I'll come back to each of these. So elasticity is about how easy it is to scale your workload up and down. And it can be quite a subtle problem. There's the technical aspect, but then there's also the human aspect. But you can make really big savings just by scaling your workloads down. So I saw a talk a while ago, and they just wrote a really simple script. And by writing that simple script to turn things off at night, they reduced the cloud bill by 30%. And this, I think we always sort of, when we talk about the cloud, we get so excited by the elasticity of the cloud, but we forget the turning it off part. We just kind of go, oh, I can scale it up, and I can scale it up, and I can scale it up. But that creates huge problems, and it creates so much waste. They tried to quantify, okay, well, how many of these servers that we've scaled up are actually doing anything useful? And they looked at 16,000 servers, and they found a quarter of them were doing no useful work. And this means that they hadn't done anything in 6 months. Like, they hadn't had any activity at all. They were completely comatose dead. It wasn't like it wasn't very useful. It wasn't like it was underutilized. It was a zombie. And they were sort of trying to figure out, like, how did this happen? Why are all of these resources being wasted? And the best idea they could come up with was perhaps someone forgot to turn them off, which is kind of sad and kind of terrible. But it's sort of, again, we get back to that behavior side, because turning applications off is really scary. No one wants to be the person who, when you have the outage, goes and says, ah, yes, that outage, that was me, because look how environmentally responsible I was trying to be. You sort of think, actually, you know what, I'll just be safe. I'll just not turn it off. Someone else's problem. It's my grandchildren's world that will go up in flames, not mine. It's all okay. And so, I think there's this sort of, particularly in a regulated industry and something with a lot of governance, it can be really, really hard, even if you've identified the workloads, to go through the process to turn them off. And so I've started to think about, like, what do we need for this to happen? And like with a light switch, you would never go into a room and look at the light switch and say, well, when I leave this room, I could save energy by turning off the light switch, but that's kind of scary. And what if I don't, what if I can't get the light back on? You just trust that it's going to work, and you know that the consequences of turning the light off are pretty low, unless there's someone already in the room, and usually if there's someone in the room, it's pretty obvious. So I think we kind of need to have that same goal for our IT systems. So systems, it should be that you can turn it off and on again, and it's fast, and that you don't have that fear, so that when it comes back up, you know it's going to come back up, and you know it's going to behave basically the same way as it did before. So you've got that resiliency in your systems. Whereas I think now a lot of systems, right, like you're like, I've got it up, I've got it working, I'm going to step away, I'm never going to touch it. If we have a power outage, that's a catastrophe because it may come up or it may not again. And I think that's how we used to be, but it's no good anymore. So I've started calling this light switch ops, this idea of having the characteristics in your system that allows you to turn it off and on again, and also actually the doing it. So far, no one else except me talks about light switch ops, but I keep waiting. If I keep saying it enough, eventually some other human being is going to say light switch ops. And we are starting to see more in this area. So a few slides ago, I talked about the script that saved 30% by turning things off. We had a talk yesterday, again, that was sort of very similar. So it was a little Quarkus application that would run in a cluster, and you could configure it to say, hey, I start work at 10 a.m. Please don't leave my cluster running overnight. And the maths that Guillaume had was that they could have their servers off for 2/3 of the time just by saying we only work 12 hours a day, which actually is quite a long time, right? Like 12 hours a day is still a long time. If you said, actually, we're going to be a bit civilized and we're going to take long lunches and we're only going to work 6 hours a day, then, well, I'm not going to do that math, but it would be almost all of the time the server would be off. So that's elasticity. The next thing to think about is efficiency. So this is about the algorithms. So this is sort of not so much the infrastructure side. This is about what we do as developers, which is, of course, our favorite topic. And our second favorite topic, of course, is why we're a better developer than the other developers. And so there's some sort of fun statistics that we can look at here about our choice of programming languages, because everybody loves a programming language war. So there was a paper that came out a few years ago. There are sort of some problems with this, but it's kind of an interesting starting point for the conversation. So does anybody want to guess what the most efficient programming language is? Yeah. C, yeah, for sure. Anybody want to have a guess at something that's very close to C? Rust, yeah, exactly. Okay, so now at the other end of the spectrum, anybody want to guess what the worst is? Oh, 2 hands, yeah. JavaScript. JavaScript is an interesting one. I think it's easy to assume JavaScript is terrible because we are Java developers. JavaScript is actually, and JavaScript is single-threaded as well, which is such a weird model, but JavaScript is actually surprisingly efficient, all things considered. And there was another hand over there. Python, yeah, exactly. So Python is astonishingly inefficient. So you can see, here's the chart. There's a few things that I think are really interesting in this. One is that we can all feel good, right? Because Java is really up there. Java is about, they ran a series of micro benchmarks. Of course, micro benchmarks are flawed. But Java was number 5. So if you're using Java, you can feel pretty good about yourself because you don't have to try and program in Rust, and you don't have to try and program in C, and yet you are still efficient. If you're using Python, you maybe should be questioning some things. But you can see as well, like, JavaScript is pretty okay when you compare it to something like Python. The other thing that's interesting is I think we usually assume that a compiled language is always going to be more efficient than an interpreted language, but you can see that Java beats Go. So on these micro benchmarks, Java was fairly significantly better than Go, just because there's so much efficiency in Java these days. So if you look at the whole table, there's the whole table. So there's some other things. You can see PHP as well, down near the bottom, obviously. See, I told you, everybody loves a language war. But yeah, and there's Java looking quite decent. But then even when you drill into it a bit more, even with Java, there's some interesting things. So there was another paper where they looked just at Java, and they tried playing around with various config parameters. And what they found was that they were able to change the energy consumption of Java by a factor of 2, just by changing the GC settings, changing various parameters. So this means that Java was about half as efficient as C, but you could double your Java efficiency by tuning it correctly, so then you could get, or actually the other way around, you could have your Java efficiency by making it worse. So, but we'll be optimistic. We'll say we can improve it by tuning it. So then the next question is, so if just changing the GC and that kind of thing can make that much difference, what difference does the framework make? So this is where Quarkus comes in. This is where today's dress code comes in. I work for Red Hat. I work on the Quarkus team. And Quarkus, sort of the strapline for Quarkus is supersonic subatomic Java, by which we mean it's really small and it's really fast. And so we've got these metrics for how small and how fast it is. And it's really, really small. It uses a tiny amount of memory, and it starts up incredibly quick. So then the question that I had when I joined the Quarkus team is, so if it does being small and light, does that translate to a reduced carbon footprint? And it turns out answering this was not so easy. In order to optimize, you have to have data. If you want to make a statement like Quarkus is carbon efficient, then you definitely have to have data. In order to measure carbon consumption, basically the way you do it is you have to measure the power usage. If you have a physical box, then what you do is you can measure it at the wall, if you actually have access to the wall. That's really thorough, but you need physical access to the wall, and you need the right equipment, and it's sort of quite challenging to integrate that kind of thing into your CI/CD pipeline or other automation, which is where you're going to want to do it. So instead, what we usually do is we use hardware instrumentation. So Intel have some instrumentation that they call RAPL. You can get the RAPL metrics from the CPU, and it will tell you, not quite as accurately as with the wall, but it will give you a pretty good idea how much power you're using. The problem with all of that is, as a really, really rough rule of thumb, the network will use same order of magnitude as the CPU. And of course, RAPL doesn't include any of the network traffic, because it can't. But there's a bigger problem, which is that usually we don't have access to the wall. Usually we're not sat next to our computer, because we have data centers and we have the cloud. And the magic of the cloud, the joy of the cloud, is that it is a black box. You don't have access to the CPU. That's what you pay them for, until you want to know what the carbon usage is, and then you're a bit stuck. There are things we can do, though, because usually you can measure the load on your isolated box. From the load, you can then use data sets to go, if I know my instance and I know my load, I can get a carbon metric, or I can get a power usage. Once I get my power usage, I know where I'm running, so I know if I'm running on coal or if I'm running on solar, and then I can get that, convert that into a carbon using the energy mix for my location. So with that, The problem with this is that each cloud vendor has slightly different methodologies for calculating the carbon in its location. So even if I know where I'm running, I can't necessarily do an apples for apples comparison. But if I want to just be optimizing, that will give me enough information to optimize. And the final thing to think about is the embedded hardware. So that's the hardware actually in the carbon in the actual hardware. Because every time you build a computer, it uses a ton of natural resources and it uses a ton of energy, and that energy is not necessarily clean. So even if you're running in Stockholm on this beautiful green electricity, the fact that you're running on a computer means there's a footprint. So all that is pretty hard. You would do that if you really cared. You wouldn't do that if you were just sort of casually trying to optimize. So there's some things that you can do that are a bit simpler. One is what I call the Vroom model. Now, has anybody heard of the Vroom model for carbon optimization? No. Nobody has heard of this because I just made it up, but I find it useful. So if you go back to that table of which languages are most energy efficient, they ran a whole series of micro-benchmarks, and they looked at the energy consumption and they looked at the time taken. And if you look at those two columns, they're basically almost the same. There's like a few bits where they don't match exactly, but they're basically the same. So that means that if you run a process and it takes a really long time to execute, it's a good bet that it's going to use more carbon than a process that's quick. So already, without doing any complicated math, you've got a good heuristic for optimizing. The other model that you can use is the economic model. So this is short for the economic input-output lifecycle assessment, which is why we call it the economic model, because nobody wants to say the economic input-output lifecycle assessment. And what this is basically that if you reduce your cloud spend, or if you're on-prem, if you reduce your hardware spend and your electricity bill, that basically means you're going to be reducing your carbon footprint. So again, without doing any complicated carbon calculations, you can use your cloud bill and trying to reduce that as a good guide to reducing your carbon footprint. If you keep everything else the same. Obviously, if you go from one kind of hardware to another or that kind of thing, then it doesn't work. These two models, if I show them to people who really understand the domain, they start to get really stressed, and they tell me that I don't know what I'm talking about. But the thing is, this is about optimizing. It's not about producing something for reporting. This is about how do we change our own workloads, how do we change our own behavior. And for that, something that's really simple is useful because it allows us to make the positive change which we should be making. So, going back to Quarkus, using those models, it wasn't actually me who did these experiments. It was Klimmel who's sat there, and I just took his work. It's not plagiarism; it's reuse. So Klimmel did some interesting experiments where he didn't want to run a micro-benchmark. He wanted to run a real workload over a significant period of time and see how Quarkus behaved and how Spring behaved. So what he did was he took Quarkus, and Quarkus can run as a natively compiled binary, or it can run on JVM. So he had those two variations, and then he had the other framework. And what he saw was that you could run Quarkus on a much, much smaller instance. So that meant that you were already saving money, which is what he plotted. But using the data sets that go from your instance to your carbon, we can see that as well with Quarkus, you're saving about half the carbon. So that's cool. But that's sort of, basically, yeah, you're reducing your carbon by half. Interestingly, native Quarkus is extremely exciting, and it's so small and it uses so much memory, it seems like it should be much more carbon efficient. What we saw in this experiment is that it's slightly smaller carbon footprint, but only slightly. So that was sort of based on a whole bunch of assumptions, so we wanted to be a bit more accurate. So we did another set of experiments where we used the RAPL telemetry on the Intel chips. And again, what you can see here, so here we were able to look at Quarkus on JVM, Quarkus on native, legacy framework on JVM, and legacy framework on native. And the further right the line is, the better. So you can see that Quarkus on JVM had the lowest carbon footprint per load. It's a little bit easier to see. So this was at a small load. If you want to increase the load, then you needed to run multiple instances, and that makes the chart a little bit clearer. So again, on this chart, lower is better. So you can see, I mean, it's really clear. Quarkus on JVM has a much lower footprint than running on native, and a much lower framework than a much lower carbon than other frameworks. So again, I was really reassured when we got these experiments because it says basically the same thing as the first set of experiments. And it's always useful, if you don't know what you're doing, to do things in several different ways and make sure that they give the same answer. So on these experiments, we saw that Quarkus cut the carbon by a factor of 2 or 3. But what we saw was that for native, even though native's memory footprint was lower, it actually had a higher carbon footprint. But the overall answer is, my starting question was, does Quarkus reduce the carbon emissions? And it was, yeah, absolutely yes. So, it saves time and it saves money because of the lower cloud costs, and then it really improves the carbon as well. When I show this, usually the first question is, that's kind of weird that native has the higher carbon footprint, because I would have thought that native would have been more efficient. When you're thinking about the use case for native, there's a few places where native works really, really well, or scenarios. So if your throughput is fairly low, or your throughput requirements are low, native is going to be a good fit. If you're resource constrained, so you want to run on old hardware, you want to run with a tiny memory footprint for some reason, then native is definitely a great fit. If you have your CI/CD really sorted out so that you're redeploying like every 5 minutes, then a Java application, a traditional Java application, will never get warmed up. So again, native is a great fit there. And of course, if you're using serverless, then it's obviously perfect. If, on the other hand, you have like a high workload, you have this high, steady workload, you need lots of throughput, JVM will work better. If your processes are long-lived, JVM will work better. If your workload is not bursty, you don't have that much elasticity, or you don't have that much need for elasticity, then JVM is going to be the best fit. This may change, by the way. The native binaries are getting better and better all of the time. So I think we did those experiments last summer. I think if we did it now, we'd see a much smaller difference. So going back to carbon, if you want to optimize carbon, it's that, which is exactly the same. So it's the same as we saw before, that if you want to optimize the carbon, you can optimize the throughput. And here, doing what is basically the right thing in terms of your workload will also be optimizing carbon. Another thing to think about with native, though, is like we've presented this like you have to choose, am I going to be native, or am I going to be JVM, and I'm going to choose once? But you don't have to choose. You can change, and you can also do a hybrid model. So one pattern that we really like is for the bulk of your workload, you have it running on JVM, because you're going to have the higher throughput. But if you have burstiness, then for that burstiness, then you want to run that in a sort of a serverless model where you scale up and respond to the burstiness. The other good thing about this pattern is it means you can under-provision, because so much waste that we see is caused by over-provisioning. Because again, nobody wants to be the person who says, well, yeah, I decided to be, optimistic with my provisioning estimates and, provision less than what we needed, because what's the worst that could happen, right? That is an awkward conversation to have. So, but with this pattern, it means that you can, be really skimpy with how much you provision, and you can still satisfy, hopefully, your SLAs. Another really cool use case for native that I do want to mention is CLIs. So traditionally, if you wrote a CLI in Java, that was not a smart thing to do. But now you can write CLIs in Java, and you can actually have a CLI that does tab completion. And every time you hit tab to get the tab completion, it starts up a native binary, figures out what your tab completion should be, and then stops it again. And to you, it's imperceptible. So this is something where I think we can take advantage of that CLI programming model while still programming in Java. And I don't have any evidence for this, but it seems like intuitively a CLI has to be a really carbon efficient way of doing things. So if you can support your users with a CLI, hopefully that's a carbon win. I mentioned that model where you have some running on JVM and some running on Quarkus. The thing with this, and particularly the thing with serverless, or with native in general actually, right, is you have this really cool technical capability, which is that you can start faster than a light bulb. But a lot of organizations, they don't want to be the one who doesn't have the service available, and they don't actually trust that it's going to come up. So serverless and native is only a benefit if you actually scale down to 0. If you're too scared to scale down to 0, then you're better off with JVM. So sort of to wrap up with Quarkus and how it helps with carbon, you get this benefit just for free. So that's like your energy usage goes down. That's really direct. It's really easy to measure. But then you get these sort of more indirect benefits as well, which is that if you have that model, maybe you could change the whole way you do your ops. Maybe you could change the whole way you do your provisioning. And instead of always provisioning for the maximum capacity, be a bit more, live on the wild side, provision for the minimum capacity, and trust that you can scale up. And if you do that, that's going to be enabled by a runtime like Quarkus, or something like Snapstart as well, or Crack. A lot of these sort of technologies that the natively compiled, or the Crack, or the Snapstart, they're going to allow you to scale up, and that potentially allows you to run in a much more efficient way. But to take advantage of that, you have to have the buy-in, you have to have the behavior, and you have to have the buy-in from the ops team and from the leadership to say, hey, actually, we're comfortable running this way. We're going to change how we do things. The final thing I want to talk about is utility, because all of this is assuming that what you're doing is useful. So often, what we're doing is actually not useful, and the most carbon efficient thing to do is to just not do it. A classic example of this is quite often when people want to listen to a song. The easiest way to get that song is to go to YouTube and watch the video. So they'll stream the video, but they won't watch the video because you just want to listen to the song in the background. So all of that data, which is really, really bulky and expensive for the video, is streaming, but it's not being used. So we need to think about that too as well, of like, do what we're doing more efficiently, but then also maybe just try and do less if it's not actually useful. So I started out with the really depressing statistics, but I think actually, there is genuinely a lot of cause for optimism, and there is a lot of cause to treat this as a positive thing. Because if you go back and you remember the Vroom model, where, of course you don't remember the Vroom model because I just made it up, but we have these mental models, and I think we need to change our mental models because we're used to thinking that there's going to be a bit of sacrifice. So like if we think about, for example, a car, I had to replace my car recently. And the car I really wanted was the car with a large engine. And when I put my foot down, it would go vroom. But actually, I was like, oh, but that would be really environmentally irresponsible, and that would be really hypocritical if I speak about environmental things while driving this car with this huge engine. So there was this sort of, oh, do I get the big end? Do I get the one I really want, or do I get, be the moral person? But we sort of understand that with cars, the faster the car, the worse it is, and the worse a person we are for driving it. And I think we kind of have the same mental model with software, right? Of like, well, if I have really fast software, then that's probably me doing a wrong thing. But actually with software, like the faster it is, the more efficient it is. Efficiency is doing more with less. So actually, by using these faster runtimes, by using these more enjoyable models, we're saving the world, and we're also, getting the benefit for ourselves. And I really like, there's this idea of a no regret solution, which again is that, it's not, I sometimes think about like, well, what's the other way to put this? So as an example, when you think about choosing your data center, if you were running in London, say, and you decide to run in Montreal or Stockholm, both of those give you much, much better carbon footprints, and they're about 15% cheaper, right? Because renewable energy is way cheaper than coal. So actually, you're sort of doing the good thing and you're getting the benefit. And we see this over and over again. So sort of, in the environmental literature, they call this co-benefits. I sometimes like to think of it as the double win, but I keep thinking, is there actually a better name for this? Sometimes we call it the win-win, or like the win squared, but then that gets a little bit unclear. Or like 1 + 1 = 3, but then you have to explain to people what you're talking about, and that is not just that you're bad at math. In the US, they would call this a twofer, but again, I don't think that really travels so well. Someone suggested that I should call it the Überwinden, which sounds really cool until you talk to someone who knows German, and then it's as bad as 1 + 1 = 3 in terms of having to explain that you're not an idiot and that just doesn't work. The extra win, it's just naming things is hard. But with all of those, the point is that climate solutions, they really, this is a positive thing. They can make everything better. So going back to the zombie servers, where they were sort of unused, the cost of that is $26 billion just last year. So if you think we could save so much money by fixing this problem, as well as saving the problem, saving the planet. So there's this huge, huge financial benefit to reducing the waste. And I mentioned this already, renewable energy, it's 9 times cheaper. So if you're hosting in Montreal, you've got 88% less carbon footprint, and it's 15% cheaper. So it's why wouldn't you do that? Well, data residency, but then you can host in Stockholm, so it's okay. And there's this project called the Drawdown Project that I really like, because they're focused on looking at the solutions and then quantifying how much you can save. And the other thing that they point out is that these are double wins. So for example, if you have, I mentioned the mental model of the car, and the big engine goes faster, but actually with an electric car, it's really fast off the traffic lights. Sometimes, when you have a heat pump, it will do your air conditioning as well as your heating. And, there's all of these benefits that you see, which is really cool. And then going back to Quarkus, obviously I really love Quarkus. I work on Quarkus. But when people try Quarkus, they come back to us and they sort of say oh, we sort of started using Quarkus because of the efficiency. But then actually we discovered it had a really great developer experience too. And again, it's this thing where you get multiple benefits, which is such a cause for optimism, I think. And so ultimately, it's not sacrifice. It's not that we have to be wearing the hair shirts and going, I'm going to do without the things I really wanted. It's that we can make the technological changes, be in a better place, and also be doing the right environmental thing. So to wrap up, definitely, if you do one thing, choose your hosting wisely. As decision makers, we can put pressure on normal organizations and also on the IT organizations. So use that buying power to say, hey, I want you to publish your ESG numbers. I want you to publish your carbon metrics, and that's going to influence me. Turn things off when you're using them, ideally with automation. Choose an energy efficient framework, because it makes a big difference. And then finally, like all of this, it's a win anyway. So that's hopefully the happy message that we can leave and go to lunch with. So thank you very much. I think we've got, oh no, we don't have time for questions. In fact, we've got 1 second for questions. Over optimistic. Thank you.